phase transformation in materials. Up to now, what I tried to communicate to you is that when you are making a material, you need a pure phase of the final product. The pure phase of the final product is required for a specific purpose. You need a specific set of properties, and that properties are known to be associated with a specific chemical formula and a specific crystal structure. And your struggle in processing the materials is to crystallize that particular phase with that particular crystal structure. By particular phase and particular crystal structure, I mean that the chemical composition of all the material is homogeneous throughout. And a specific crystal structure is that a crystal structure can be cubic. A specific crystal structure can be tetragonal. It can be triclinic. It can be orthorhombic. The cubic will have one sort of property. The tetragonal will have different sort of properties. The monoclinic will have different sort of properties. But that particular properties which you need are associated with a specific phase. As I was telling you in my last lectures, that for example you have the DTA plot like this and like this. This means two phases are forming in this material. If, for example, this is the cubic phase and this is the tetragonal phase, then you will heat the material at this stage. If you need the tetragonal one. If you need the cubic one, then you will heat the material at this particular temperature. Usually, it is not possible that when you heat treat a material, for example, for 2 hours, and it doesn't form the required phase, then you will have to go to 4 hours, then you will have to go to 10 hours. People heat treat materials for 30 hours, 40 hours, a week, or like that. There are some materials which are not transforming easily to the required phase. For that purpose, you heat treat the material, check it, the phase is not pure, again grind it, mill it, powder it, again heat treat it, again grind it, powder it, and again heat treat it until you get a pure phase of that material. When you get the pure phase of that material, then you look into the density. If the material is, for example, you are making pottery ware, a dinner set, it is not important whether it is pure phase or it is highly dense. For example, if it is 80% dense, it can work, because in the everything should be thought as a scientist. What are your expectations from a pottery ware pot? You can wash it, so it is resistant to the detergents. This is one property of the cooking pot or the water drinking pot or whatever you want. It is washable. Washable means when you use a detergent to clean it, it doesn't erode with that. It doesn't react with that. The detergent does not remain in the pores of the body. So you are drinking clean, hygienic water, which is good for health. Secondly, the pot is completely impermeable. When you put water or liquid in it, it doesn't infuse into the body and it doesn't go out of the body. This means it is impermeable. Impermeable means the water droplets cannot permeate through it. Thirdly, it is of the desired shape, right? So for the first thing, resistant to chemical detergents, you need a shiny surface so that there are no pores where the detergent particles can stay. And for that you need some phase which melts at that temperature. Which melts at that temperature when something, if the body is like this, and this is roughed up, and when detergent is used, you wash it from the top, but at some corners the detergent can stop. When you melt something, it homogenizes the surface. But the question is, why are you not melting the whole part? If you melt the whole part, then it will not be, its shape will not be retained. Its shape will work. It will distort, right? So when it distorts, then your purpose is not met. Your goal is not met. So you need something solid which can retain its shape, right? But at the same time, some part of it melts so that all the pores are filled, right? Impermeability needs melting. What scientifically it tells you? The overall body is solid, right? The overall body is solid, but the surface is impermeable. And the simplest example of this is that when you make walls in your house, you lap it with very fine, fluent clay slurry. The hatu nare robal banitasu agaliuke. Right? This lapping means you make the wall impermeable. If the wall is rough, the water will infuse into it. If the wall is smooth and impermeable, then water will not enter the wall. So this is the same thing here, right? That you make the surface like a lap, and that is called glazing. Glazing of the material. You prepare the shape and form of the body in solid, then you put it in that slurry and heat treat it. The body material is melting at high temperature, and the lapping, the glaze, melts at relatively lower temperature. So the body is not affected and the surface is melted, and you get a chemically resistant surface of the part. Permeability inside the body is stopped by partial melting of the initial ingredients. You had clay, feldspar, and quartz. This phase is melting at relatively lower temperature. This phase is melting at very high temperature, and this phase is melting in between the two. So when you heat treat the material, you partially melt the material. So the material was particles like this, and these pores and voids were causing permeation of the liquid. And by partial melting, you filled these pores, and the material became impermeable. Right? So this means that if you are bringing current, communicating current from Tarbela to Peshawar, and 1 millimeter piece of the wire is insulator, then no current will come. Right? It will disconnect the electricity line. The same thing is true for telecommunication devices. Your material is 50% dense. If it is 50% dense, then what happens? 50% of the material has, for example, a dielectric constant 5000, which is the material which you intend to make. But the voids and the open spaces has the permeability or dielectric constant of free space, which is 1. So the total permeability will decrease to half, right? To avoid that, because all the applications, or you can say most of the applications, need purity of the property. If you use 1 gram of a material and you are expecting 5,000 dielectric constant from it, then it must give the 5,000 value. If it is giving 2,500, the material is not usable for that application. And that is why I was telling you that phase purity is very, very important. So from this differential thermal analysis plot, you know about which phase is forming at what temperature and for how long treatment. DTA doesn't tell you that. DTA gives you an idea that the material will form at this temperature. The phase will form. The phase will crystallize at that temperature. The DTA gives you a clue. DTA is like a person standing in the way on the road, and you ask him where is Peshawar University, and he tells you this. Then you have to go to this direction. It doesn't mean that go to the end of the earth, but you should have a logical thinking that what is the next technique I can use. Then heat the material at different temperatures, at the same temperatures for different time intervals. Carefully, I am telling you very important point. Heat the material at the same temperature for different intervals of time. Because if a phase can form at, for example, after 5 hours heat treatment at a specific temperature, and you are heating it for 2.5 hours, this means you didn't make the actual phase. If you heat treated the material for 15 hours and you form that phase, this means you wasted energy. So that is why people do trials and errors, and people heat the material as a researcher for several time intervals at that specific temperature, and when they find the phase purity, then they take that temperature as the optimum temperature. Optimum temperature means the best temperature, the most suitable temperature at which that particular phase forms. Now, within this peak, there is further a lot of information. Are you interested in 100% conversion of the material? Are you interested in 50% crystallization of the material? Are you interested in crystallizing small crystals? Are you interested in crystallizing large crystal? Again, your DTA is telling you that. How? If you heat treat the material at the peak temperature, this peak temperature, heat it for 2 hours, and you will see big crystals of that material throughout the volume of the glass. But are you interested in big crystals? If you are interested in electrical properties, then you need minimum grain boundaries, because the grain boundaries enhance the power loss. Grain boundary technically, scientifically, is a different phase, because the behavior of the material in the middle of the grain is different than the periphery or border of the grain. So this means that if you are interested, for example, say polarization, then when the material is throughout homogeneous and you heat treat it at a specific temperature, it will polarize homogeneously. But when you have large crystals, the orientation of crystals becomes, the reorientation of crystal becomes difficult. When the reorientation of crystal becomes difficult, What does this mean? You need more energy to polarize that system. When polarization becomes difficult, this means you need more energy. So energy wise it is not feasible. So you want small grain size for polarization reversal, because the whole science, the application, and I will specifically say electro-optics physics, it is totally playing with the single electron or electron cloud. The whole science, what the mankind has so far learned and taught, circulates around that electron. The whole properties, electrical, they come from the behavior of that electron cloud. And I frequently tell you in my talks that if I have this is not electrical circuit. It is the gulal with which you hit birds. If this rubber is loose, it has no capacity to do work. If this is the nucleus and the surrounding is the electron cloud or electron orbit, right? If this cloud is spherically symmetric, if this electronic cloud around the nucleus is spherically symmetric, it can do no work. If it is not spherically symmetric, this means it is polarized. When it is not spherically symmetric, it is polarized. And polarization means it will respond to the electric field you apply. If its response is quick, it will require less energy. If the response is not quick, it will require more energy, right? And that is the whole game of science. And that is the whole game. You are moved from the classical physics, from the classical engineering towards nanoscale engineering and nanoscale physics, nanoscience and technology. The main thing